Hi everyone, my name is Owen Bendel and I'm going to present our ACL 2022 paper, Quality Controlled Paraphrase Generation, a joint work with Ranit Aharonov, Michal Shmuley-Shor, Ilya Schneiderman, Noam Slonim and Liat Endor. In this talk, I'm going to show you how you can control the output quality of a text-to-text model simply by conditioning its behavior on the required quality. If you can measure the quality of your training examples, you can simply add it as additional input in your training procedure. Then at inference time, ask the model to generate with higher quality. Additionally, you can utilize this method to safely learn from automatically correlated mixed quality data without losing control. Focusing on paraphrase generation, I'm going to tackle questions like how to train text-to-text quality controlled model, to what extent you can control the quality, and how to avoid impossible quality requests at inference time. In paraphrase generation, our task is to rewrite a sentence with different words and structure with as little changes as possible to its meaning. Following this definition, we measure the quality of paraphrases at 3 dimensions: lexical diversity, syntactic diversity, and semantic similarity. Higher levels of linguistic diversity, expressed in lexical and syntactic diversity, indicate on higher paraphrasing quality, as long as it comes, of course, with high semantic similarity. Followed by previous works, we use bag-of-word distance to measure lexical diversity, tree distance on the constituency parse tree for syntactic diversity, and BLERT model for semantic similarity. For simplicity, all scores are normalized to a range of 1 to 100. We took 3 different datasets containing clusters of semantically related sentences. For every semantically related pair of sentences, we measured the 3 dimensions of paraphrasing quality. For every example, we quantized the 3 dimensions of measured quality and represented each level in each dimension with a special token. We then fed a pre-trained encoder-decoder model with 3 quality guidance tokens together with the tokens of the input sentence. Then, we used autoregressive cross-entropy loss to train the model to predict the target sentence. To this model we called QCPG, Quality Control Paraphrase Generator. At inference time, we can feed QCPG with different quality constraints as we wish. But how do we choose the right quality control values? You might think, let's ask for the highest quality possible. But some combinations of high quality demands are not even possible to achieve. For instance, when trying to gain lexical diversity, you might want to change every word. But nouns like pizza are very hard to change without loss of meaning. Since trial and error is not scalable for large batches, we need to find an automatic solution to identify what is the highest quality demand that is achievable. For this purpose, we trained another model we called Quality Predictor, or QP, predicting what is the most likely achievable paraphrasing quality for a given sentence. The values the model predict we term the typical paraphrasing quality. At this point, we assume that for different sentences, the distance between the typical quality and the maximal possible quality is different. But still, there is an offset from the typical quality that is globally safe to be asked from the generation model without pushing a request that is impossible to achieve. So once we predicted for every sentence its typical paraphrase quality, we can add to the prediction a fixed global offset that increases the quality demands we use as constraints for QCPG. From now on, our problem is what combination of offsets are appropriate for each dimension. But before we find the optimal offsets, let's take a quick look at the behavior of the model as a function of the quality offset. When we increase the offset from the typical quality in just one dimension while using no offset in the other dimensions, we can see great responsiveness in the manipulated dimension. For instance, in the bottom row, we ask QCPG to generate with increasing semantic offsets while keeping the linguistic constraints at their typical values. We can see across all datasets that the semantic similarity between the generated paraphrases and the origins indeed increased. All in all, while leaving the other dimension of quality relatively unchanged. We can also see that when asking for very high quality offsets, the models suddenly break and fail to satisfy the increasing quality constraints. This supports our assumption that we can find a global combination of offsets that can push every paraphrase beyond its typical quality but still remain in the achievable area. So how do we find the right quality offsets? We suggest to take a held-out validation set and evaluate it at every possible combination of offsets. We created heat maps representing the success in preserving meaning and achieving linguistic diversity scores as function of the offsets. With the help of those heat maps, we can identify optimal offset combination for a given policy. For example, we looked for a combination of offsets for a policy we call QCPG star. In QCPG star, we want semantic similarity levels that are just slightly better than a baseline, but with as much as possible linguistic diversity. With the aid of the heat maps, you can easily identify the optimal offset combination for this QCPG star policy. When we automatically test the performance of QCPG star on an unseen test set, we see two interesting trends. First, QCPG star achieves better results at each dimension than the classic fine-tuned baseline, trained with the same number of parameters and exactly the same training examples. The second and quite surprising trend is that most of the time QCPG star achieve higher qualities than the average quality at the training data. We conclude that QCPG can learn from data of mixed qualities, but then at test time can present, upon request, high quality behavior. In the table below, you can see paraphrases from different datasets and those generated by QCPG star. In most cases, paraphrases generated by QCPG star are better both in the semantic preservation and the linguistic diversity. We also conducted an extensive human evaluation to verify that the semantic similarity is indeed better in our model than the baseline. Our results show that QCPG star produces paraphrases with significantly better semantic faithfulness quality. While being a very effective method at controlling output quality, quality control models has still room for improvement. Our results show that the model is responsive to the control, but not all the time. Our current research is focused on methods for tightening the control power, either by pre-training text-to-text models with the notion of quality conditioning, or using reinforcement learning methods to enforce the quality control requirements. Contact us if you find it interesting and exciting as much as we do. If you are interested in all the fine details and some more interesting results, we encourage you to read the paper. Thank you for watching.